So let's talk about performance metrics. Okay, so we're going to come back again to the binary case, simple case. And this is essentially shows you what can happen in binary classification. So here's the true label. Here is our prediction of it. So there's 4 cases it can happen. Either the true label was 1, prediction was 1, we call this a true positive, or the true was 0, prediction was 0, we call that a true negative. But then we have 2 different ways to make errors. Truth was 0, prediction was 1, that's a false positive, or the truth was 1, we predicted 0, that's a false negative. Okay, so false positives, sometimes people call them false alarms or false negatives, they call them misdetections. So in some applications, there's really not a lot of difference between these two types of mistakes you can make. So for example, if I'm sending you a stream of like millions of bits in a digital communication system, you don't really make a distinction between mistaking a 0 for 1 or 1 for 0. Those kind of errors are more or less the same because in those applications, they're very symmetric. On the other hand, in some other applications, there's a huge difference between these 2 types of negative errors. So let's consider cancer diagnosis. You take some tests to determine if you have cancer or not. The test is never perfect, so mistakes can happen, right? So on one hand, if you get a false positive, in that case, you're told you have cancer, but you don't. You know, you're depressed for a little bit, but it's not the end of the world because you're going to have more tests done, and eventually you'll figure out, oh, I don't actually have cancer. On the other hand, if you have a false negative, meaning you do have cancer, but the test said you don't, now you live your life. Meanwhile, the cancer grows inside you, and by the time that more symptoms appear, you take another test, it may be too late. Right? So in this cancer detection, these are very different. They have very different ramifications, and you really want to weight them differently. You don't want to say that they're equal. You want to think of them as different outcomes, different types of error. So that kind of motivates different ways to measure performance in classification. So the most common way is to measure the accuracy. And there you are making essentially no distinction between these 2 types of errors. You're just saying, how often is it the case that the truth equals the prediction? We can think about it in terms of this table here as follows. Imagine that these are just counts, like you did 1,000 experiments, and so then you record the outcomes, and so those 4 numbers have to add up to 1,000. And so given this table of outcomes, sometimes it's called contingency table, or we'll often call it a confusion matrix. What you could do is you could estimate the probability that of correct by saying, okay, how many times was I correct? So you add those 2 numbers, divided by all the cases. So you add those 4 numbers. Okay, so in this case, if you want to measure accuracy, you're just measuring how often is the test correct. So like I said, there's some applications like digital communications where that's exactly what you want. But if you're doing cancer diagnosis, accuracy is really not the metric you want to be looking at. Okay, so here's some other metrics. Precision is what is the probability that the truth is 1 given that you predicted 1. So in this medical situation, you could say, given a positive test, this one, how often is the patient actually sick? Another thing people look at is recall, where you swap the order. So in this case, you say, given that I have a sick patient, how often is the test correct? How often is the test positive? Okay. And as we'll see, you can sort of trade between these. You can make one arbitrarily good by making the other bad. And so you have to be careful in how you balance these 2, and we'll talk about that in a moment. So neither of these on their own are giving you the full story. So there's different ways to try to combine them into a single score. And probably the most common is the F1 score, where you take the inverse of those 2, you average them, and then you inverse that. So this is a harmonic mean of precision and recall. And at the end of the day, now you just have one metric which tells you how good you're doing. And this could be maybe a lot more meaningful than accuracy in some applications. Okay, so these are common in machine learning. Now in medicine, they sometimes use different terminology. So they use sensitivity. This is identical to recall. But then there's specificity. So here, it's given a healthy patient, how often is the test correct, versus given a sick patient, how often is the test correct. Okay, so these are all ways that people measure things. Machine learning, like in scikit-learn, it has easy ways to do this. I don't think scikit-learn talks about these, but you can imagine why they're relevant. So one place where we see this kind of stuff happening is COVID testing, right? Because COVID tests, again, are not perfect, but there's a difference between giving a false positive and a false negative, right? There's ramifications to both, but they're quite different. And so when they design COVID tests, they have to think very carefully about all these issues and weigh things out, and they design the tests in a very particular way so that they get, so that the balance of the types of errors is what they want. Okay, so that's performance metrics for binary classification. Any questions on all these definitions? Okay, so here's how you do this in scikit-learn. It's actually very, very easy. So when you do your cross-validation and you give it a score, typically in the past we'd give it like negative mean squared error, or R squared. Now you can give it any one of these, precision, recall, F1, or accuracy, or you can actually give it a set of scores, all 4 of them, and it will do the cross-validation and measure all those different performances. And then you can extract the results, compute means over the different folds. And just as an example in this breast cancer demo, we have precision, recall, F1, accuracy. They're all in the 90s. And here we even have the standard errors, which we can compute looking across the K different folds, K-fold cross-validation. So the point is it's pretty straightforward to do all this in scikit-learn with those 4 scores. Okay. Okay, now I mentioned before that it's possible to trade off between precision and recall. So this is generally how we do it. So remember that when we do all these linear methods, it's a 2-step procedure. In the first step, we, so given our test vector x and our trained weights b and w, we compute a score. That's going to be a real number. So 0 typically means like, I really don't know. Positive means I think the label is 1. Negative means I think the label is 0. And, so we talked earlier about quantizing it, but actually when you quantize it, you lose information, right? You lose something about the confidence that is present in Z. So one way to get that confidence is to just plug it into the logistic model, which actually gives you a probability. And this is just a model. It's not a correct probability, but it tells you some guess of what is the probability that y equals 1 given Z. So that's a number between 0 and 1, and that can be very useful. Here I'm calling it a confidence. It's also often referred to as a soft decision. So confidence or soft decision. Now, at the end of the day, though, you need to make a decision. Is this going to be, is y going to be 1 or 0? And so that's when you finally have to convert it to a hard decision. But now, one way that you have some flexibility is essentially where you quantize it. So until now, we focus on quantizing at z equals 0, which would correspond to a probability of 0.5. Right? We said if z is 0 or larger, we say that we return label 1. If z is less than 0, return the label 0. Or equivalently, if the soft decision was 0.5 or higher, we return 1. And if the soft decision was less than 0.5, we return 0. And in fact, that choice is the right choice if you want to minimize the error rate or maximize accuracy. That's exactly what you want to do. But we said that there are applications where we may not care about accuracy directly. We might care about precision and recall. And so here's an example of what happens when this threshold t changes from 0 to 1. Your precision goes up and your recall goes down. In fact, when t is 0, then essentially you're always selecting y hat equals 1. Always. Right? So it's a trivial case. And in that case, your recall is going to be perfect, but your precision is going to be worthless. On the other hand, if you go the opposite way, if you set t all the way to 1, you're always going to be returning a 0. And so in that case, it's flips. And so by adjusting t, you can actually make whatever trade-off you want between these two. You can do the same thing with sensitivity and specificity. So here is specificity goes up, sensitivity goes down. So you can trade off between these just by not really changing your logistic model at all. Everything there is identical. It's just how you use it at the end, how you make those hard decisions. And this T might be very application dependent. And so it's nice that you can design your model, all of that, without thinking about the application. And only at the very end, when you're applying it, you have to make that choice about T. Okay. And so here's another way, similar, very similar in spirit. Oh, yeah.
When you say T equals 0.5 minimize the error rate, that is only for the training data, right? Maybe for the unseen data.
So I guess, yeah, it's a good question, exactly what happens with the unseen data. But I would say, like in general, when you have a given objective, which is to maximize accuracy, you usually want to do this both on your training data and on your test data, let's say, right? So now, the accuracy, the training accuracy tends to be higher than the test accuracy, usually because you're going to be overfitting to your training. But now, if you just measure, like, how do both of them change with the threshold t, I think you would see a similar behavior where as t goes to 0.5, you end up getting the best training and the best test, more or less. And so it kind of goes together, training or test works this way. Okay, any other questions on this? All right, so another way you can see a trade-off is you can look at the true positive rate versus the false positive rate. So here's a plot, slightly different trade-off. So as the threshold goes up, so when the threshold is 0, what happens is you're always going to be selecting y hat equals 1. So both of these are sort of trivially maximized. And then as your threshold goes up, both of them come down to 0. But still, you can see that there's sort of a different behavior. One of them goes down really quick, the other not as quick. And so the way that this is most commonly plotted is you plot what's called the receiver operating characteristic, which is a plot of the false positive rate on the horizontal and the true positive rate. And where you want to be is in the top left corner, where both of those quantities are large. And where you don't want to be is on the bottom right corner, where both of them are, wait, let me see. Sorry, I said that wrong. You want to be up here where your true positive rate is high and your false positive rate is low. So you don't want to be making any false positives, but you want to be making lots of true positives. The worst case is down here, where your true positive rate is low and your false positive rate is high. Okay, so all the way there. So all of these different points in the operating curve correspond to different choices of the threshold t. So as t increases, based on this plot, as t increases, you can see that your true positive rate starts high and goes low. So it starts high and goes low. So that's what happens as t increases. Meanwhile, your false positive rate is moving like that. So by choosing t, you can choose where you are on here. Maybe you want to be here, maybe you want to be here. In many cases, maybe your boss tells you, look, the maximum false positive rate I will tolerate is 0.1. So just give me the best true positive rate for that constraint. And so you end up drawing something here and you say, okay, this is where my model is. But in some cases, you actually want to measure the performance of your model without someone telling you exactly which threshold to use. So you don't actually know where you're going to be. So you want a threshold-independent performance metric. So the way that that's commonly done is you just look at the area under the curve. The area under this curve, like the larger that area is, the better, right? Because as I push this curve closer and closer to that, its area increases. Maximum area is going to be 1. So in general, you see AUCs of less than 1. But this is a nice way to measure the performance of your model that does not require you to make any specific choice on the threshold. So this is very commonly used in literature, this stuff. And how you do this in scikit-learn is pretty straightforward. So in that log reg method, there is a predict probability, which gives you soft outputs on your training samples here. And then with metrics.ROC curve, you can compare the true labels to your predicted probabilities, and it will give you this false positive rate, the true positive rate, and thresholds. So give you basically what you need to plot this. And if you want to compute the area under the curve, you have this metrics.ROC AUC score. Same inputs, and it gives you the actual area under the curve. In this case, it's pretty close to 1, 0.996. Not perfect, but pretty good. Okay, so although we're almost done with the unit, there's a little bit more to talk about, and I think we're done for today. I don't want to hold you any longer, so we'll finish up with this. So yeah, start your studying. Post any questions you have to the discussion boards, or bring them to office hours, and yeah, we'll see you on Monday. Have a nice weekend.